to the Bio 110 podcast. I hope you all had a great spring break and are feeling recharged because we're diving into one of the most fascinating parts of biology this week. Trust me, you don't want to miss it.
Oh, absolutely. Cells are, well, they're literally the foundation of life. Everything we are, everything we do, it starts with cells. I'm really excited to kick off this module with you all because honestly, this is when biology really starts to feel alive.
Haha, good one, Dr. R. All right, before we get too deep into the science, a quick heads up for everyone listening. Mark your calendars for April 14th because that's when your next exam will take place. I know it sounds far off, but blink and boom, it'll be here.
Exactly. And listen, it's so important to stay on top of the material, especially with something as detail-packed as cell biology. I always tell my students, don't cram because cramming only leads to forgetting.
Great advice. Because it'd be pretty tough to cram what? About 1 trillion facts about cellular processes in one night.
Easily 1 trillion. Joking aside, you don't want to miss the chance to truly understand this stuff. We're going to explore topics like how cells grow, how they divide, and even how they sometimes don't when they try to break the rules. Does it sound intriguing yet, Neil?
It does to me. So stick with us this week, folks. All we ask is that you stay curious, just like Dr. R over here, and keep up with the material bit by bit.
Yeah, because biology, it's not just about learning facts. It's about seeing the connections, like why this matters for tissue repair, reproduction, and even for some, understanding how cancer develops. It's truly mind-blowing.
All right, let's get going. You ready, Dr. R?
Born ready. Let's take a closer look at how life builds from the tiniest building blocks, cells.
So, as promised, let's dive in. Cell division. This is where biology gets truly dynamic, right? It's like the orchestrator behind everything from growth to healing. Pretty cool, huh?
Absolutely, right? Without cell division, life would come to, well, a screeching halt. It's how single-celled organisms like bacteria reproduce and make new individuals. And for multicellular organisms like us, it's all about growth, replacing damaged tissue, and hey, tissue renewal.
Right, like how our skin cells keep regenerating? Wild. Didn't you say we shed 40 pounds of skin in a lifetime?
Yep, on average. Think about that for a moment. That's 40 pounds worth of cell division happening over time, with some of those skin cells flaking off as we walk around, sit down, even as we sleep. It's amazing when you consider how constant and efficient the process is.
Okay, hold up. You mentioned chromosomes earlier. What's the deal with those? And wait, isn't there also chromatin and chromatids? I mean, that's, one too many chromas for me.
Haha, I get it. It's easy to mix those up. Here's the simplest way to think about it. Imagine you've got a deck of playing cards. Each card in that deck represents genetic information, okay? Now, a chromosome is like taking part of that deck and bundling it into a tight, organized packet. It's compact and clean.
All right, so like a deck with a rubber band around it.
Exactly. Now, chromatin is what the DNA looks like when it's all loose, like when the cards are shuffled all over the table. It's unorganized, but still crucial because that's usually when the cell is doing its day-to-day work. Before dividing. When it's time to divide, though, the messy pile, the chromatin, gets packed up into those nice, tight chromosomes.
Okay, I'm following. And what about chromatids?
Chromatids are where things get even cooler. Imagine you take one card and make an identical copy of it, like a photocopy. Those two identical copies still joined together are called sister chromatids. When the cell's ready to split, one chromatid goes to each new cell, like dividing the deck evenly.
That is a ridiculously neat system. But why does the cell bother with all this bundling and copying?
Oh, great question. It's all about precision. Bundling the DNA into chromosomes helps the cell organize and move massive amounts of genetic material quickly and mistake-free. Imagine trying to gather loose strings versus picking up neatly rolled spools. Clear difference, right?
Gotcha. So chromosomes basically make sure we don't end up with a big tangled mess every time our bodies grow or repair something.
Exactly. And, we're constantly juggling that balance, making identical cells through mitosis for things like skin renewal and creating cells with half the genetic material through meiosis for reproduction. That's where the magic of genetic diversity comes into play too. But let's stick with basics for now.
I love it. Something so tiny but so meticulously planned. Cell division is like nature's ultimate choreography.
Oh, I like that. Cell division as choreography, because it really is. Every step is deliberate, synchronized, and meant to keep life running smoothly. And speaking of steps, next up, we'll break down how cell division happens in phases. It's all about the cell cycle.
Okay, Dr. R, let's step onto the stage of this cell division choreography and break it down. What's the cell cycle all about, and how does it pull off such a flawless routine?
Oh, this one is a classic in biology. The cell cycle is like a blueprint for life. It's how cells grow, copy themselves, and eventually divide. It's organized into phases, and it all starts with interphase, where most of the action happens.
Okay, interphase. Got it. What's happening there, though?
So interphase has three sections, G1, S, and G2. G1 is where the cell grows and checks if everything's right to move forward. Then comes S phase, where it copies all its DNA. And finally, G2 gives it another chance to build and prepare before the big moment. Division.
Wow, so G1 is like the cell's quality control, huh? That checkpoint sounds pretty crucial.
Exactly. The G1 checkpoint is a big deal. It's where the cell decides, should I divide or not? If something looks off, it can pause, repair the issue, or even exit the cycle entirely by entering something called G0, the rest phase.
And what happens if that checkpoint fails?
That's the real kicker. When checkpoints mess up, cells can start dividing uncontrollably. That's how tumors form. The beauty of checkpoints is they're like traffic lights. Stop, go, wait. But some cells just blow past the reds, and that's when things go haywire.
All right, tumors, let's get into it. I've heard benign and malignant. What's the difference?
Great question. A benign tumor is kind of like a troublemaker that stays in its lane. It grows but doesn't invade or spread. Malignant tumors, though, they're on a whole other level. They don't just grow uncontrollably. They invade other tissues and can spread throughout the body in a process called metastasis.
Whoa. So malignant tumors are the ones that really raise red flags?
Definitely. And the key is that these are just cancer cells that have ignored every stop sign the cell cycle throws at them. Instead of pausing for repairs or stopping, they keep dividing and dividing, disrupting everything in the process.
Yikes. So basically, this whole system of checkpoints is like the unsung hero of our body, keeping us safe from things going totally off script.
Exactly. And it's why understanding this process is so critical, not just for biology, but for medicine too. Diagnosing where the checkpoints went wrong can literally save lives. It's like finding where the house of cards started to wobble before the whole thing collapses.
That's fascinating and honestly a bit mind-blowing. So we've got interphase, checkpoints, and tumor behavior covered. What's coming up next?
Well, next, we're getting into the action-packed bit, the mitotic phase. It's where all that preparation pays off. We'll explore prophase, metaphase, anaphase, and telophase, and trust me, it's like the grand finale of cellular choreography.
All right, here we go. The grand finale of cell division. Dr. R, you teased the mitotic phase as this culmination of all the preparation. So give us the scoop. Why does this phase matter so much?
Because it's how everything grows, Eric. From the moment we were formed from just a single cell, mitosis has been the blueprint that allowed us to become, well, us. It's precise, it's fascinating, and honestly, it's nature's most spectacular copy-paste mechanism.
Copy-paste, huh? All right, let's break it down. What's step one in this slick operation?
Step one is prophase. Picture this. The DNA, which has been chilling loose in the nucleus, suddenly gets its act together. It condenses into those tight chromosomes we talked about earlier. Meanwhile, the centrosomes, kind of like command centers, move to opposite ends of the cell, creating a structure called the mitotic spindle. This is essentially the ropes that are going to divide everything neatly.
Okay, so it's all about organization right now. What comes next?
Following prophase, we hit prometaphase, a transition phase. Here's where things get serious. The nuclear envelope, the membrane around our DNA, breaks down, giving the spindle microtubules access to the chromosomes. Specialized structures called kinetochores attach to the spindle's ropes, kind of like hooks ready to haul things into place.
Let me guess. This is where tug of war begins?
Exactly. And by the time we hit metaphase, all the chromosomes align in the center of the cell, along this neat imaginary line called the metaphase plate. It's a critical checkpoint. If it's not perfectly aligned and hooked up, the cell won't proceed. That's how we avoid errors in the next step.
Wow, I didn't realize this process had that level of quality control. So what happens once everything's perfectly lined up?
That brings us to anaphase. This is the moment of truth. The sister chromatids, those identical DNA copies, are pulled apart to opposite sides of the cell. Kinetochores act like little Pac-Men chomping away at the ropes, shortening them so the chromatids get hauled to their destinations. It's like watching synchronized swimmers execute the perfect routine.
All right, so now we've got a room divided. What's next?
Next is telophase, where the cleanup begins. The chromosomes reach their respective sides and uncoil back into their relaxed state. Meanwhile, two new nuclear envelopes form, one for each side, marking the official creation of two nuclei.
And does this mean we're done? Is the division complete?
Almost. After telophase comes cytokinesis, the final separation. For animal cells, it's like a string wrapping around the middle of the cell and tightening until it splits into two. Plant cells, though, have to take a different route. They build a new cell wall from vesicles right down the center. The result? Two independent cells, each ready to carry on the work of life.
That's incredible. Plant cells building walls. It's like construction on a microscopic level. Okay, so before we wrap this up, what's the big takeaway for all the mitosis newbies out there?
Mitosis is precision in action. It's growth, repair, and maintenance all rolled into this beautifully orchestrated process. Every one of us, every multicellular being, relies on mitosis to keep us alive and thriving. It's the cell's way of saying, let's get this job done right.
All right, that's a wrap on cell division. A massive thank you to Dr. R for walking us through one of life's most fascinating processes. And to all our listeners, I hope this gave you a new appreciation for the little marvels happening inside us every single day.
This was so much fun, and remember, folks, if this sparks any questions about biology, keep exploring and keep asking. Science is at its best when it's collaborative.
Couldn't agree more. Thanks for joining us, everyone. Until next time, stay curious, stay inspired, and we'll catch you in the next episode of the Bio 110 podcast. Take care.